Okay, hey everyone, I'm Ayelet, and this is Yael sitting here on the first row. We are from SciSense, and today we're going to talk about our natural language querying interface and how we integrated it with our knowledge graph. Okay, so first few words about SciSense. SciSense is an Israeli company. We are developing a business analytics platform. We have now more than 800 employees all over the world. And our goal is to empower builders to deliver insights in such a way that users can achieve better business outcomes. We have a full stack platform, which means you can take data from anywhere, from high-performance databases such as Snowflake or Redshift, or from Google Analytics or Salesforce, mesh all these sources together into one data model, and by this, simplify your complex data. And on top of it, you can build analytics. For example, you can build a SciSense dashboards. Here you can see an example for how a SciSense dashboard looks like. And we are about to launch very soon a new feature. It's called Simply Ask, which is our natural language querying interface. And the idea is to allow users to ask questions in English. We're starting with English, but in the future, we're planning to extend it to other languages as well. And I would like to start with a short demo of this feature. Okay, so here you can see SciSense dashboard. This is the interface. You can write your questions. Here you can see our autocomplete capabilities, which Yael is going to talk about later. And get the results, switch between visualizations. Okay, let's continue. Okay, so natural language querying is one of the oldest disciplines in artificial intelligence. The task is to translate a natural language sentence into a database query language. In most cases, it will be SQL. The task is also known as NLQ SQL. And the idea is to make business intelligence and data exploration more approachable to all people, even to non or less technical persons. There are two main approaches in the literature to NLQ, natural language query. The more recent one is deep learning, and the more conservative is the NLP pipeline approach. In the deep learning world, there are two famous NL2 SQL benchmarks. The first one by Salesforce is WikiSQL. It is crowdsourced annotated, and one of its disadvantages is that it includes very simple SQL queries. The more recent one is Spider. It was annotated by Yael students. And one of its advantages is that it includes more complex SQL queries. And also, a very important advantage is that it's trying to make NLQ more generalized in such a way that you can ask questions on your trained model that on databases you didn't train on. And they are doing it by separating the train and test sets in such a way that it won't be on the same databases. The questions won't be on the same databases. Here you can see some of the considerations we took into account when we needed to decide which approach we want to implement. So of course, the deep learning approach has many advantages. Just to name one of them, it's more scalable. But on the other hand, it requires a large training set, and unfortunately, the benchmark I presented now are not good enough for us. the wiki SQL, the queries there are not complicated enough for our needs. And the size of a spider, we believe it's not big enough to create a good production-ready system. And also on top of it, on Sisense, we don't use SQL. We use another query language, which is called Jackal. It's JSON-based. And in most cases, the transformation between the languages is not straightforward. So it's not easy to convert this data set to be suitable for our needs. And also, our users are business intelligence users. And their questions have, in many cases, different characteristics. For example, they are more focused on time-related questions, such as last year, last quarter, and so on. So eventually, we decided to go with the NLP pipeline approach, which is much more easier to control and to explain. And explanation was one of our one of the major thing it was important for us. And we mainly use the approach presented in the constructive and interactive natural language interface for rational databases paper. Okay, so if we want to simplify the pipeline we implemented, we can divide it into 3 steps. The first one will be text pre-processing. After that, n-gram classification, and lastly, building a query sketch. In the text pre-processing step, we're applying tokenization, lemmatization. We are parsing date and numbers in such a way that users will be able to ask questions such as sales last week, on Christmas, and so on. And we used Duckling, which is a package by Facebook written in Clojure. It's a very good one. And we also use the part of speech tagging. So for example, a typical question can be, show me the 10 categories with the highest total incomes on Black Friday 2019. Okay, on the next step, we're classifying n-grams into database and query elements, such as table names, column names, values, and query elements such as top filters, date filters, and so on. So just to give an example, if we're continuing with the last question, categories, for example, will be matched to the column category, highest will be matched to the top filter, total to the aggregation function, and so on. And to do this, we're using 3 mechanisms. The first one are spacey matchers. We are also applying fuzzy matching, and we're using distilled BERT to detect synonyms. So I would like to start with the last one, with the synonym detection. So we are using word embeddings from distilled BERT to match synonyms to database elements. Here you can see as an example that amount was matched to the column quantity, and United States was matched to the value, USA was matched to the value United States. And to do this, we're calculating similarities between word embeddings using cosine similarities. And we have a predefined threshold that when the similarity is above this threshold, we are taking it as a match. One interesting thing that we found out is that when we're trying to match gibberish words, we're getting very high similarities just to any random words. So to avoid it, we're just considering only dictionary words. Another mechanism we're using are the spacey matchers. These are very strong matchers. They have 2 types. The first one are phrase matchers that allow you to match a very large list of phrases on your text very efficiently. And they also have the rule matchers that you can define rules, kind of similar to regexes, but you can use properties from spaCy, such as a part of speech and relationships between the tokens. So I brought here as an example one of the rules we're using. The goal of this rule is to detect patterns such as top and bottom, filters, as I showed before. And this rule can contain up to 3 tokens. The first token is optional, and we expect it to be a number. The second token should be with a specific part of speech, which are superlative part of speech, and another optional token of a number. So, for example, using this rule, we can find out patterns such as 5 highest, longest, cheapest. And to determine the direction, if it should be matched to top or bottom, we're also using word embeddings and calculate the similarity between the match and the token large and the token small, and just taking the one with the higher similarity. So, for example, 5 highest will be matched to top, and cheapest will be matched to bottom. And also, this can give us a hint to the column. For example, cheapest can be matched, of course, to the bottom, but also to the price column. Okay, and lastly, we're using dependency parsing trees to match between the elements we classified earlier. So, for example, if we have the sentence, show me the sum of costs and revenues in 2019, here you can see the parsing tree. And using heuristics and rules, we can see that sum, for example, should be applied both on costs and revenues. Also, one thing that it's important to notice that natural language queries can be very ambiguous. And just to give you 2 types of ambiguities, tokens can match to more than one database element. For example, if the user writes product, we can match it to product name or to product category. And what we're doing when we have more than one match, we're creating all possible permutations of the matches. And the issue is that it can grow exponentially, and we don't want to build all the query sketches based on this. So we are using ranking, using some heuristics and usage patterns. We're also taking from the knowledge graph, which Yael will talk about later, and just limiting the number of permutations. And another type of ambiguity can be in this visualization. For example, say sales in Australia and Germany, we can present it as just one number, as you can see here, or as 2 lines broken by years and countries. Okay, so I presented one component of the NLQ system architecture, which is the NLQ pipeline. We have 3 additional components. One of them is the autocomplete query, which is our recommendation system of the NLQ. And Yael will talk now about it and how we integrated it with our knowledge graph.
Hi, hear me all right? So my name is Yael. Here, okay. So as we all know, recommendations are everywhere. We encounter them in our everyday life when we choose what route to take, what colleagues to connect, what friends to follow, what to watch next, and what items should we buy. But at the basis of a good recommendation is to understand the users. So what does that mean? Sorry? Yeah, I'm okay. What does that mean at Sisense? At Sisense, the data that is important for us is the user's metadata. We're interested in understanding how our users interact with the product. Here's an example of a dashboard. A dashboard is a collection of widgets. Every widget, like you already understood, represents some question. So here's an example of a pie chart. The underlying question in this example is, show me the total revenue broken by gender. So as you can see on the side, you have two query items in this example. One is total revenue, which is an aggregation on the revenue column, and another is a group by on the gender. So from one single query, we actually have a lot of data. We know who asked the query. We know what the query is. We know what items make up the query. We can also know how to connect the different query items between each other and connect them to different queries asked. For example, if someone filters in his query by United States, so that's a filter on country, we can connect that to a different item in a different query where country is the group by. Each query item also points to at least one database element, which is the column and table in the database. And of course, the database is connected to the user's environment. On the other hand, a query was asked from a widget, and the widget lies inside a dashboard, which is a context for all the questions in this specific dashboard, and this context was defined by the dashboard designer. And lastly, a dashboard also has dashboard filters, and these are also connected. So if we take all these usage patterns from our users and we collect them, we can store them in, you guessed it, a graph. So why use a graph? Well, first, with the explosion of data in the past years, graphs are becoming a lot more popular now. Gartner termed them as an emerging technology in its report. I love this example by Ed Finkler that showcases how important graphs are for querying. So it goes like this. If you're an analyst and you want to know how many people who bought a toaster live in Kansas and have a criminal record, use the coupon in yesterday's paper. So if you were trying to answer this with a relational database, you would say, no, get the hell out. It's a really ugly query. But actually, if you have all this data modeled in your graph, it's very easy. And with a few single hops, and you can get the answer. Next. Okay, so graphs are built from a collection of nodes in relationship. A graph can have multiple node types. In this example, we have a person and a company. Nodes are connected to each other by relationships. You can have one type of relationship or multiple relationships in the graph and for each node. Both can hold properties. And relationships can be directional or not directional. Also, another big advantage for graphs is that you can alter the schema really easily. So if you have more data to model, let's say in our case we have a new data source and we want to connect users to user role, it's very easy to add this to our existing graph. In addition, graphs today, you can perform many of the machine learning tasks you're all familiar with. Three major ones are classification, link prediction, which is predicting the relationship between two nodes, and community detection, which is clustering on the graph. Also, state-of-the-art algorithms, including graph embeddings and graph neural networks, are becoming more and more popular on graphs. Okay, so here's an illustration of Sisense knowledge graph. We have many node types. You can see the users here, their user role, what user groups they're in, what questions they ask, and what dashboards and data sources, and so on. We can also tell if a single user explores a widget, they're actually drilling down and asking additional questions, and we can follow that and really understand what the user is doing. Also, we've done some research on topic extraction, on the textual data from the queries themselves, and we can cluster these topics and cluster what our users are actually doing. So back to the awesome feature Ayelet showed you before, the autocomplete query. Let's go through a few examples. So you opened up this feature from an existing dashboard and you started typing total sales by gender. And then you get a few types of recommendations. One is fully contained. It's really straightforward. You'll see what query contained in the past all the input items you just gave and return the other items. We can also generate new queries by finding a query that has a partial match to the input items and returning those. And we can also return out-of-context information, which will return items that are not in the dashboard you're actually asking the question, and thus enriching the questions you can ask. How do we evaluate such a model? So using the same example, start typing total sales, you get 3 recommendations. You liked by gender, you clicked it, you got more recommendations, and you didn't like them. And wrote by yourself by brand, got a few more recommendations, and you're content with the query, and stopped here, you pressed run. So this is really straightforward. We gave 3 recommendations. 2 of them were in the final query, and we can score our recommendation. We can also penalize lower ranking recommendation. If we recommended, if a user actually liked a recommendation that was lower ranking, that means we didn't recommend well. We should have recommended this item higher up, and we'll penalize our score. Okay, so I hope I convinced you that having a knowledge graph is a great basis for understanding your users, and it's a great basis for generating many types of recommendations. Here's another cool feature we're working on, which is called Topic to Dashboard. It's a similar setup to NLQ, but here a user doesn't have a dashboard. He's just connected to his data source, and he starts typing a topic in natural language. This topic will be represented with some word embedding. And on the other hand, inside the graph, we have embedded vectors of all the queries other people asked. Just to emphasize here, this is a universal knowledge graph. It holds all the metadata of all our accounts. And then we can match the similarity between the topics and the queries asked. And let's say we retrieve 3 widgets, and those are the ones we want to recommend. So now we have another problem. These widgets maybe belong to other data sources, so you can't just return them to the user. The query will fail. So we have to do some projection work here and make the transformation between the data source elements in order to build this query. In order to do that, well, I'm not really going into it, but this is a teaser to another thing we're working on. We want to track data lineage, so that will help me know and to connect our users' tables. This is a link prediction task, so we can connect 2 tables that we think are the same table, but we're not sure. And so if we connect them, that will make the projection task easier. Another nice task is a classification task for all our users' role. We don't know what their role are, but if we would have a labeled set, we can classify and then later segment our users by roles and achieve better recommendations. And just we're short in time, so I'll go to the last one. We also have the database elements. Another nice project is to define the hierarchy between the elements, so you can link between region and country and city and define a hierarchy. And that will also be a nice AI feature for our users. to help them drill into a question in a very organized manner. All this work is a joint work between from Sisen's AI research team, Chen and Amnon are the two data scientists that worked on this with us, and I think they're here. We had a really fun time working on this together, and I think we're really doing all these AI features that democratize the business users and builders of these systems has a lot of impact, and I'm happy to be part of it. Thank you.